just to go over kind of some announcements real quick. Starting next month, we're going to be moving our meetup from 9 to 10, from 8 to 9. I sent out a survey and a lot of people said that moving it up a little bit earlier would make it a little more accessible. So we are going to do just that. We are live streaming today, and we'll be live streaming all of our sessions going forward. And then I will have the edited videos kind of up within a week. I'll trim out all of the stuff where we're just sitting and talking for the first bit. And then last but not least, I'll be posting all the slides from Technology Advice and Chris to our Slack, and then I'll also be posting it up in the Meetup. And last but not least, if you are not in our Slack yet and are interested in getting more into our community, please reach out to me and I can get you added to our Slack. We have a lot of conversations there around data science, projects we're working on. There you go. All right, first up is Technology Advice, and I will drive for them and let them take it from here.
So I think Shailene sent you a few slides, nothing like overly important other than just who we are and a little bit about what we do. So I'm Catherine Phones, work upstairs on the top floor at Technology Advice. These guys that came in with me, this is Kevin and John, they're on our business intelligence team. Perfect. Yeah, there's your faces.
Sorry, wrong one. There we go.
So we're super excited for the opportunity to sponsor this morning. Just learned about you guys, I think, through doing some recruiting and online searching. So happy that you were close and in the same building and we could hop down and say hi. Technology Advice is, we say that we connect buyers and sellers of business technology. What that really means is we do telemarketing and email marketing. We do connect buyers and sellers. So what that looks like is if you're a technology buyer, say you're in the market for a new business intelligence tool, you can come through our website, compare products, read reviews. Then you can actually also talk to a technology advisor who will really talk you through a more in-depth conversation to make some recommendations for you. On the flip side of that, we also have large technology companies who come to us, think about the HPs and Dells of the world that come to us and say, hey, I've got these great new servers I'm trying to, take to market. I need to talk to, IT decision makers. And so we have a massive database that we call and email into based on the targeting they've given us. We can ask custom questions on the phone around project timelines, budgets, what's a pain point with their current solution. And then it's lead gen. So then we're selling those as leads to the Dells and IBMs of the world. So we have a lot of data. It's very dirty at the moment. We haven't always had the best team around it. We've been, for the most part, like a one-man data team for a very long time. So we've officially formed the business intelligence team. When was that? Back in, I guess when Kevin joined the team back in like May, June timeframe. So I've been focused on building it out. We've got a lot of big goals as a company over the next few years around our data and how we use it a little bit more intelligently. We still will do lead gen, but we want to get out of the rat race of, turning on a campaign for Dell, getting those 100 leads and turning it back off. So there's a lot of cool things that we can do with it. We just haven't figured out what yet. We know we've got a lot of it, but we just don't know what to do yet. So I'm going to hop back upstairs for some other meetings, but I think these two guys are going to stick around and enjoy the presentation today. Feel free to ask questions. I'll leave a couple of business cards if anybody wants my number or email. But check out our website, see what we're all about. We're hiring actively, so holler if you're interested or just want to learn more. Thanks.
Thank you. All right. So without further ado, we will get started. Come on. There we go.
Hey, so my name is Chris Harvey. I'm a self-taught reinforcement learning expert. I've been doing it for about 1.5 years now. I've been going through a lot of it. Go ahead.
Oh.
Yeah. So I'm gonna quickly talk about the history, not too much, and then go through some of the differences, like misconceptions between reinforcement learning and the other disciplines, and then go through some, what actually is it, how does it work, and then some notation and whatnot, then end it with some deep learning. It's going to be interesting. And then I don't think we're actually going to be able to get to a Q&A if I go long-winded and give too many examples, but, so ask questions whenever you want. If you don't understand something, ask me. It's not going to interrupt my flow, so. So the founders are mainly Bartow and Sutton. They wrote the foundational book back in like 1988, A lot of people don't know this. Reinforcement learning is actually the oldest form of machine learning. It was made back in the early 50s, so it was a decade before the perceptron or supervised learning. So that's very interesting. And it came from animal learning in psychology. So Bardo had that was his background in psychology, and then he was like, hey, how do animals learn? And then they went through different things, and then someone came in with control theory and how to find optimal policies. So then they're like, okay, how can we mesh these things? And it wasn't until Watkins, who's really only done one thing in reinforcement learning, was just writing a book on how to use TD learning. And then they combined it all, and it just came this really sophisticated model. And then, so the real difference is I'm assuming you all know what supervised and unsupervised learning is, just general classification and, finding hidden features for unsupervised learning. Reinforcement learning is different because it's an agent interacting with an environment, and it has this form of long-term rewards. And then it also has a goal that it's trying to accomplish. So it's not just classifying, it's trying to come up with a solution for a very specific problem. And the real difference, I don't know how many of you guys know about evolutionary models, but they're models that it has a problem it's trying to solve, but usually it just has one metric it's trying to optimize, which is fitness. And that can kind of get bogged down to where it'll get stuck in a rut. And through random mutations of the best model that has been produced, it'll have a bunch of children, and then those children will compete, and then the next best child will be selected, and have more babies. And it continuously does this for hundreds of generations until it has a sophisticated model. But one of the best things about reinforcement learning is it has a long-term goal. So here are two different examples, and these are different paths for the same goal. And genetic algorithm, the evolutionary model, will see something really attractive at the beginning, but not realize at the end it has a really bad payoff. And then reinforcement learning will try a bunch of things, even if it has a bad early start, and it will continuously go until it finds something better. And that's one of the strengths of reinforcement learning, is it can go over the hurdles of plateaus. So here's something I came up with last night. I was really happy about it. Reinforcement learning is an agent with a goal, interacting with an environment, and learning from experience. And that's the foundation of all reinforcement learning, is just that sentence. So let's break that down a little bit. An agent.
So that's the acronym.
No.
Yeah. AGELE, Agile.
Of course.
That's pretty good.
Yeah, totally did that on purpose. An agent is typically has two different functions, and has a value function, which is the goal orientation. That's what gives it the long-term rewards. Every time it makes an action or every state, it'll get a feedback from the environment. And then over time, it tries to optimize that whole list. So it tries to add all the rewards together, and it optimizes that. And it has a policy function, which optimizes how the agent interacts with the environment. So it has two different brains. One of them is like, okay, that felt good, I'm gonna keep on trying to do that. Then the other one's like, how did I do that? I need to remember how to do that and get better at it. So it's two different learning at the same time that's added together. That's why it's really powerful. And then a goal is whatever we decide the agent to do. And then the agent can decide on its own. It's called curiosity learning, which I'm not really going to talk about, but it's super interesting. I'll talk about it at the end if you guys have questions. And it is shaped by rewards that we manually set typically. There's all sorts of ways to do it. Interacting means the actions the agent is able to take, not just what it does take, but it has all the possibilities of different actions. Then off of a thing called a Q table, it has probabilities for each reward of the actions and just goes through them. The environment is the world in which it lives. Environment is very hard to define in a lot of situations because what the agent actually is a bit tricky, especially for like robotics. And learning is the feedback it gets and also the policy. So it learns two different things at the same time, and it tries to optimize both. And then experience is its memory, everything it's done, all the states it's seen, even the things that it's considered, but it hasn't actually done. Any questions on that?
That's pretty good.
And here's some notation. This is not the full list of notation. There's 100 different variables in reinforcement learning. This is just a couple of the most basic ones. I'm only going to really cover these three in the discrete and policy. So states, actions, rewards, what the model, what the environment it sees, what actions it takes, and the reward it gets is really all reinforcement learning is. And then discrete time steps, which part of the process is in currently, which one's before and after it. And then policy, we use V policy and Q policy to determine the value function and the policy function. So even though we use the same character for both, it's, I don't know why they did that, honestly. But, and here is the process itself. So this is called a Markov decision process. It was made by people way before them, but they adopted it and like, hey, it's pretty cool. The agent sees a state, so the reward isn't there yet. So at the start, it's just an agent in a state. It makes a decision. The environment is changed by the state. It measures the change, and then we give it a reward off of the change. And it continually does this process over and over again, and it learns from trial and error, just like a human. One important thing to note is it does not try to improve rewards. So it's not hedonistic. It's not just like, hey, that candy tasted really good. I should eat that a lot. It's, what do I need to be healthy? So it tries to improve the overall value, not just the current value. And what is an agent? The agent is what is controlling the environment, what changes the environment. So to define it, we use this thing called an agent environment boundary line. And that's sometimes really easy to describe. It's like in stock trading, the agent is the thing that makes trades and buys, sells, or waits. In robots, it's difficult to explain because what part of a robot is the agent, what part is the environment? Typically people think the whole robot would be the agent. That's not true. The agent is just the CPU, just the thing making decisions. All of its gyros, servos, its legs, limbs, any part of it is the environment. It's making decisions that move those things, and that interacts with the reality. So if you're training a robot to walk, you train it to use its legs, but it doesn't know what legs are. It just sees that as the environment. Like a baby, it's learning how to walk. Humans have this intrinsic idea that we are one unit, and this is the agent. That's not really, it's not reality. So you learn how to use your body to enact with the environment. It's kind of interesting. And then you have these two functions again. Value function, of course, the goal, and the agent itself seeks to improve it, specifically for model-free environments, which we'll talk about a little bit later. And the policy function, this is where deep learning comes in a lot, is the neural networks that you can attach to reinforcement learning help it learn the actions it makes to take a lot better because you can do gradient descent and it just learns smoother. It's a lot easier. So what goal can we give the agent? We can give it positive or negative rewards. And that is the reinforcement part of reinforcement learning. If you discipline a child, if you give it candy or you spank it, that is reinforcement learning. We accomplish it, so you can give it rewards per time step. Let's say you want to finish a maze, and so to do that, you want it to do it really quickly, right? So you give it a negative reward for every state that it's in. So it tries to minimize its negative rewards, and it tries to finish quicker. If you're saying conditional rewards, let's say you have a grenade, there's an enemy coming, you want to blow up a tank. You want the agent to throw the grenade before, like right at the tank. You don't want to throw it before or after. So you give it really huge penalties for when it misses. But whenever it's correct, you give it a big bonus. So it knows, okay, that was good. Let's keep on doing that. And then you give large rewards on completion. So you do not get trapped in suboptimal situations. That is where people try to get to finish the race. And it's good to get those turbos because it makes you go fast. So there's points involved. What they did was they gave a larger bonus to the turbos than they did to finishing the level. So it just got caught in this infinite loop, just getting points constantly. And it never does finish. It's really stupid. Don't do that. That's bad. So here's a good example. Whenever it's trained properly, whenever you have a right reward system, you want to see this gradual decrease in error loss. And this is stuff that I did myself. That is bad. So this is when I kind of made a stupid algorithm where it didn't really have much of a brain, and it's very unstable. Like that was within the first time step. It should not jump around like that. And then by the 1000th, it was just a black line. There's nothing there. The agent can learn in two different ways. So again, it tries to optimize both policies at the same time. And the way it can optimize the value function is it tries to make predictions about the reward it's going to receive. And then it also observes the actual reward it gets. So based off of those two differences, it subtracts it, then it applies it to a learning rate constant, which is alpha in this sense. And then you can get do gradient descent and reach the optimal solution that way. Because all reinforcement learning will converge no matter what, which is a really good strength about it, is it will reach 100% efficiency given enough time, but usually that is thousands of years or millions of years in some cases, and you don't want to wait that long. I mean, you can if you want, but you're going to be dead, maybe. So not good, but usually it can reach optimal solutions or at least usable solutions within a couple thousand time steps, so you don't have to wait the millions of years. It's really good. And then neural networks can help it learn quicker. So there's these, each action and state pair is called a Q value. That's what the policy function tries to optimize. And for every pair, there's a Q table. So each action it's ever taken, it keeps it in a record. And then it calls back on its memory. It's like, okay, Mario's about to hit a block. What should we do? Should we jump? Should we walk into it endlessly? Which is really dumb. I trained a genetic algorithm that actually did that for hours, just walked into blocks. So annoying. This fixes that. So it adjusts weights all the time to reduce the error, just gradient descent. So you can do like atom, attograd, all sorts of gradient descent methods on both policies. It's really nifty. And we can also use a discount parameter to make the agent actually consider short-term rewards valuable. Because if you don't, then you can see over time, if this policy is gone, every reward is calculated at the same level of value. So what the agent does is it continuously tries to live to die. It only focuses on the end goal. It only focuses on death. It doesn't try to expand its life. It doesn't try to achieve more during life. So to fix that, they came up with this thing called a discount factor, which we use gamma for. And here's the actual notation for it. Whenever the starting state's 0, just to give it really hedonistic ideas for the first state. And then as it improves, it keeps on reducing and reducing and reducing because it's expletive. And then that's basically it. So if you have it at 0, that of course deletes itself. At 1, it's gamma to the first, that's just itself, gamma to the second, and so on. And then you sum up all those together, and that is your value function. So this is just the way value function is defined. It's fairly simple when you think about it. You can do a lot of interesting things with it. If you have it, so you can set constants on it as well, which a lot of people typically do. If your constant is 0, the agent will never get past this first step because everything times 0 is 0, right? So if you have it set to 0, it'll only recognize the very first step. If you have it set to 1, it'll recognize all steps equally. So people typically set it to like a 0.8 range, just trying to get it to where it is still future-sighted, but it doesn't completely dismiss the present. So it tries to get it to live in the moment a little bit it's like saving money, essentially. And then here's all the different ones I could think of. There's a ton more, but here's the basic ones that most reinforcement learning agents, like these are the models that it's modeled around. You have 3 different states that you can have problems in. So you have a discrete time step, which is just a finite amount of moves, like a chess game, for example. Whenever I was training my chess engine, it learns kind of well. And for like the maze example, you want it to do it in the least amount of time steps possible. Or you could have something a little bit more interesting, which is the robot example I'm going to get to in, I think, the next slide. Yeah. Then you have a continuous time step, which is a prolonged finite time step. So it's just very, very long. It's like, what's a good example? I thought of them last night, and I just cannot remember them. Continuous time is blanking. Let's go back to it. Infinite time series is like stock market trading. It's usually the most difficult to manage because the environments usually change without the agent making a change, which is extraordinarily difficult. So it's the unpredictable, everything you don't want to actually deal with. I'm not doing research in that. I respect the people who do. Not for me. That is a little above me. Continuous time steps we typically use for kind of stock trading. If you do it, like if you count every day as an example, so you trade continuously all throughout the day, then the market closes. And then you sum up all the reward for the day you got. So at continuous time step, you can break down in multiple ways. You can either break it down per action that's done, so they get rewards every action they make, or they get rewards every time step, so like every couple minutes, every couple seconds. For stock market trading, it's every minute that the market refreshes. That's really what determines what models you use, is the discrete versus continuous. Most models work with infinite time steps, except the discrete only ones. So then you have the environments, which also depict. So there's about 20 to 30 different algorithms you can use in reinforcement learning. So the main two that really make a difference is this two and these two, because those are the most use cases. And the games against nature is like a robot learning how to walk. Its nature is the environment, and it doesn't have any opponents whatsoever other than gravity. And it learns slowly. That's usually the most stable. It's usually the fastest to train. Games against opponent can be very quick to train, because you can have, if they have the same goal and you're training both of them, they can learn at the same time. So if I have a tic-tac-toe example where one agent learns how to win, one agent learns how to lose, that's valuable learning for both. So you have twice the training speed, where whenever something loses, it tries to optimize on how not to lose, and if something wins, it tries to optimize on how to win again. So you have this competing faction. Games against itself is kind of hard to describe, but it's more like how can it improve its own hardware functionality, I guess. So like how can, like bodybuilding, something like that. So how can you improve yourself by taking from the environment, but not actually changing the environment that much? And then games against multiple opponents is very difficult if they don't share the same goal. So that's where stock trading is very difficult. It's actually what I focus in, is financial reinforcement learning. With stock trading, you have a bunch of different agents, and you can either consider them as different agents or part of the environment. And that's a little bit tricky. So which one do you want to do? Do you want to optimize to where you can predict your opponent, or do you want to optimize to where you try to predict unpredictable actions from the environment? And either way, it's difficult because you don't have shared goals. Their goal is to make money, your goal is to make money. Those don't overlap unless you both make money, but it's rare. So you have to not only predict the unpredictable, you have to predict something that has a different goal than yourself. And then games with teammates, which is easy, but it's tricky. So there's this example from AI or OpenAI. They train robots all the time virtually, and they train robots how to play soccer. So they train them how to stand, how to walk, and how to kick a ball. And if they all have the same exact goal, they become very selfish, and they all run at the ball together, and it kind of becomes a mosh pit. They're all just kicking each other, and the ball runs into each other. To fix that, you could say, hey, we want you to play goalie, we want you to play defense, we want you to play offense, and you can kind of have a team structure. A lot of people don't think about that, surprisingly, so they just have mosh pits all the time, and it's really annoying to deal with because I'm usually the guy that has to go in and clean code. So types of rewards, you can either do sparse rewards, which is it's semi-predictable to where you don't actually know when you're going to get rewards. It's typically from taking actions in an unpredictable environment. That's a lot of the use cases that are for the real world, like driving. Your sparse rewards are whenever you don't get in an accident, whenever you make it to a destination, whenever you stop at a red light. You don't actually know how far those red lights are going to be whenever you're learning. So that's where the sparse comes in. And then instant rewards is where it comes in at every time step. So the maze example gets a negative reward every move it makes, or if you get a reward for every action you make, that's also instant. That's the easiest to do. It's what most simulated and programmatically, like that's what the most use case is just instant because it's easy to do. And then random rewards is very difficult. That's the stock trading. You don't know when you're going to make money. You don't know when you're going to lose money because you don't know what's going to happen. So that is awful to program. Delayed rewards is easy as well because it's just, you only get a reward at the very end. It's very easy to optimize, but it's hard for the agent to learn because it doesn't have any feedback whatsoever for every the actions it's choosing. So for a chess example, it only learns if it's won or lost. If it draws, it doesn't really learn much other than what made it draw. And I put a slight negative reward on draws. I don't just make it neutral because you don't want to actually draw, you want to win. against high-level opponents, it's kind of hard, especially for stuff like checkers, where it's a solved game where if they both play perfectly, they're going to draw no matter what. So I typically try to still get them to win. And in doing so, the good thing about value functions is it can go back and it can see, okay, I made this change and it still gave me a positive reward. Genetic algorithms just look at fitness and they don't know what decisions it made. It just knows that fitness got higher. It can't see, okay, Mario jumped over that block, it ducked under that Koopa, it threw a shell. It can't see that. All it sees is, oh, my fitness went from 1,000 to 1,200. Reinforcement learning can see that. It can follow a search tree, it can follow the Q values, can say, hey, this Q value was higher than that one, it led to a better outcome. That's really one of the strengths of reinforcement learning. And then two-way rewards is what I was talking about earlier, the game against opponent, where one person wins or loses, or they have two different outcomes but a shared goal. So they're both updating the algorithm at the same time. Is there any questions about any of this? Kind of went through a lot.
So the delayed reward. So you said it was easy to optimize. Is that why you would go for it?
Most of the time it's very easy. So it converges quickly.
It converges quickly.
Yeah, so the biggest problem in reinforcement learning, well, the two biggest problems is exploitation versus exploration. How can you get the agent to explore the environment naturally? And like you said, the complexity. Because there's two different types of complexity. There's complexity of design, and then there's also complexity of computation.
Right.
And the convergence, it will always converge, but you don't want it to take decades. You want it to be quick. So doing simple rewards that are easy to calculate makes it faster.
Okay.
Yeah. Any other questions?
As an experiment, the
Mhm.
delayed reward. So how would it know to change? Let's say the final outcome is given, right?
Mhm.
And it only knows the final outcome.
Yeah.
But it doesn't know anything in the middle.
Yeah.
How would it change? How would it change things?
So there's this thing called a transition probability. So it looks at all of the available Q actions, at least for Q learning. It looks at all the available actions and it has values from past experiences. So as it does the experience more and more, it learns more about the outcome, and then that is optimized. So every decision it makes, it keeps a value stored in its own memory, and then it'll eventually just optimize it.
And so it takes the maximum, which is the
Mhm.
intuitively smart thing to do.
Yeah.
But that means it's not exploring.
Uh,
So there's also a probability
Yeah.
that it'll take a lower value,
you can.
take an action that it has seen as a lower value, but that would be an exploration,
Yes.
right?
Yeah. So the problem is, how do you balance that? How do you balance the best value? So doing E4 is a really good example in chess. It's a good move, but what about G2? What about moving the knights? So it tries to explore all the different openings, because most reinforcement learning, you're not teaching it anything. You're just saying, hey, this is the environment, go learn. You're not giving it prior knowledge. You're not giving it a lot of things in supervised learning. For chess example, you can teach it openings, you can teach it closings, you can teach it maneuvering and all that. You don't do that in reinforcement learning. It learns by itself how to do that, and sometimes even better than what humans can program. Like Alpha Zero learned how to play chess better than Stockfish 8, which is all of humanity's combined knowledge of chess, and it beat it in 4 hours. So 4 hours of training from no knowledge whatsoever, trained for 4 hours, it was better than all of human.
But that wasn't a laptop. That was
No, it was $1 million machine that Google built. It used, I think, 200 TPUs, which I don't know if you would know what a TPU is, but the new graphics cards that just came out have TPU chips in them. Oh, they're fast. I think someone in the thing has 2 of them.
Tensor processing.
Yeah, tensor processing unit.
Specific for doing all the tensor.
Yeah. So it does matrix multiplications very quickly.
That's nice.
Yeah. Oh man, it's 100 times faster than GPU. Yeah. I want a 2080 Ti so badly.
They're expensive. I'm looking at building a deep learning box, and I want to get that. I'm not sure if I can work out the 1400 for one
Yeah.
of those.
I'm getting married in a month, and I'm like, oh, that's expensive. And I want to build a machine that's $4,000. And I'm trying to tell my future wife, hey, can I have this? And she's like, hey.
No,
So-
that's the mistake. You're not buying it for yourself. You're buying it for her. But
Yeah.
she really wants it.
Oh,
She
yeah.
just doesn't know it yet.
Oh, yeah, she's definitely going to play Minecraft on it. It's going to be great. Yeah. Any other questions? All right. So here's a good example I found in the book by Barr and Sutton. So I'm totally copying this and changing it a little bit, mostly copied. So we have a robot named Wally, no relation. A robot whose job it is to pick up trash, again, no relation. It has a rechargeable battery with 3 states, high, low, dead, and it can do one of 3 things at a time. It can either search around for trash, it can wait for a human to bring it trash, which is unlikely, or it can go home and recharge, which doesn't really do anything other than fill its battery back up. So picking up trash, we usually give a reward of +1 unless you want to give it a higher reward to incentivize it more. Waiting does nothing, recharging does nothing, and running out of battery gives a -3 because we don't want it to do that. Every time the robot searches, it uses some of its battery at a probability because, you use your phone for a minute, it only reduces it so much. So we have this thing called a probability transition where it's just the state minus a probability of the battery decreasing so the agent can learn how its battery decreases. And then, so what is the optimal policy and how would it typically learn? Like what would be the actual way the robot would learn? And here's the different combinations. These 3 are invalid because you're not gonna wait and go from low battery to high battery just magically, and cases like that. So it would experiment with searching and it would do it until it died because it doesn't know better. So then you have to go out, collect your robot, recharge it, tell it bad robot, it does it again, you're just angry. The way to solve that is you can give it a higher negative reward for losing its battery because you don't want to pick up your robot every time it dies. So instead of a 3, you could give it a +100. It would become afraid of exploring that. So you want to balance the fear mechanism of it getting a negative reward versus the actual exploration mechanism of searching. So you want it to search eventually after searching enough times and seeing where humans are. Like let's say this is on a campus. It would learn the times of day that the class is out. It would go to the places with a lot of humans and it would be really cute. So people would bring it trash and be like, oh, here you go, little robot, and feed it. And then it gets a reward and it's happy. And then whenever humans aren't there, it would probably just wait. It would just not use its battery because it knows it's not efficient. So after probably, a couple of years of learning in real life, if you're not doing simulated learning, it would eventually get to this really high efficiency where it knows where to go, how to do it, how to coerce people into giving them like, hey, go finish off your bottle, give it to me, I'm cute. So that's how reinforcement learning really works. It learns from experience. It learns from dealing with the unknown in a very sophisticated way. So here are the problems that we are typically trying to improve, which is, as I said earlier, exploration versus exploitation. The hardest problem in reinforcement learning, the only real problem in my opinion. The way the agent creates goals. So how can we do feature engineering to determine the goals it wants to do? That is also difficult, especially in new domains that we don't have any experience in. That's why the research is so slow in the area, even though it's also so old. And then computational speed is also a huge hurdle. And every new model typically tries to improve at least one, and it always tries to improve exploration versus exploitation. I can't think of a single model where it didn't improve it and it just improved the other 2. So let's talk about the exploitation versus greed, as computer science calls it. So greedy agent is one that just does the best possible path all the time. That was what the original back in the 60s is what the things would do. They were just greedy. So they came up with this thing called an epsilon, which is a stationary value. So it's the amount that it's going to do random exploration. So you can either have it be stationary, where 20% of the time is typically the value, but it can do 10 to 30%. 20% of the time, it'll make a move that totally random, it has no idea what's going to happen. Then 80% of the time, it'll try to do what it knows is best. So over time, slowly, it'll learn better. But when you have a stationary reward, it learns slowly because it tries to only do the best thing majority of the time, and that doesn't really give you better results because you want to explore to get better results. So in my opinion, the best way to do it is epsilon decay. That's the only one I use. I've used optimistic too. It's good, but not nearly as good. The higher your value of epsilon, the quicker it learns, but it's very shallow learning. So if you do epsilon of 1, it'll learn very quickly and then baseline at 30% optimum. And that is really bad. That's what greedy does too. Greedy learns very quickly, and then the highest it's ever gone is 36%. Standard epsilon usually gets to like the 80% range. Epsilon decay usually gets in the high 90s or the mid 90s. And you can have this thing, it's essentially just a parameter. You change the percentage. I'd change the percentage every 0.5%. And then you just multiply that by the decay value, and over every iteration, it slowly diminishes and diminishes and diminishes until you're set with. You can either let it go infinitely and just diminish to like 0.01, or you can set a limit. That's what I do. I set my limit to 0.01 because the lower your limit, the better it can learn. So the more optimal it becomes. So you have this kind of trade-off to where do I want to learn quickly or do I want to learn a lot? And epsilon decay kind of bridges the two. It's great. Optimistic is another really interesting thing. It has this idea of bias where you can either make it optimistic or pessimistic. Pessimistic makes it explore nothing. It makes it really greedy. Optimistic makes it very exploratory because if you give it a high initial starting value, it won't be satisfied until it finds a reward that is better than that. So it always tries to optimize its reward. If its reward is +5 at the beginning, it won't settle for 2 or 3. It'll always try to get like a 6. And that can be really good. It learns slowly at first, but it has a very high cutoff. It's typically better than stationary epsilon. The modern day deep learning usually just uses epsilon decay. We don't use any of the other ones just because they're too specific use cases. You can't use optimistic in continuous or infinite time steps. You can only use them discrete. So it's really good for stuff like solving a maze or doing something simple, but it's not super good for later uses. Then upper confidence bounds. I don't know if this is a typical computer science algorithm. It's applied to reinforcement learning as well. Basically, it keeps a summation of all the rewards it could possibly do. And then it looks at the new reward and it's like, okay, is this better or worse than the past rewards? And if it hasn't done it before, it has a really high negative bias. So it has like a 0.5 that's multiplied by. So as it continually does the same reaction, that bias decreases. So as it explores its environment, it is more comfortable with the environment. If you have a bunch of restaurants, you go to all of them to see what you like. You're not sure about a couple, you go to it one more time, you're like, oh, that was awful. Never go there again. Doesn't unless someone forces you to, which you can do. But you typically find what you like and you exploit it. You like 3 restaurants, you go to those 3 restaurants. And if a new place opens up, you might try it once. It's good. It's the most general of them. It applies in every single use case. It's very nifty. It's not better than optimistic or epsilon decay, but it's one size fits all. It's like Java. Any questions? No? All right. Here are some charts of the different exploration mechanisms. So the green is a very low epsilon, and you can see it learns lower, but it will eventually completely outpace it. It's not even comparable. That's epsilon 0.1. That's a greedy function. It does nothing. You can see it baselining at 36, and it will never get better. I don't know why, it just stuck there. The lower the epsilon, it will always be better in the long run. So what you can do is a decay. I don't know why I don't have a thing of it, but decay makes it learn this quickly, and then it completely goes up. So it just is a great curve. And here is a UCB, so the confidence bounds versus epsilon 0.1. And you can see that it kind of spikes in the beginning as it's trying all the different places. It's very happy with some of the places, so it learns quickly. And then it tries all the bad places, and it's like, oh, this is awful. Then you get reality sets in. You're like, the world isn't always great. And then it goes back down, and then it's like, okay, maybe it's better. So it keeps on trying the places it likes, and it gets more and more better. And then this is the optimistic value, where again, has a very high start because it's very happy about life, and then it's like, oh, nothing I do is better than my base reward, and then it gets depressed, and then it slowly gets happy again, and it goes back up. So it just depends on the use case. If you want an algorithm to learn very quickly or be reliable quickly, like a self-driving car, you don't want it to have that happen. You don't want to crash into things. You don't want to kill people. So you have to do something a bit more stable than the fancy methods. So here's the main difference between algorithms is you can have a model that acts as a simulation of the environment. So instead of having the agent learn from experience, it learns from prediction. So it simulates the reality. So let's say you're stock trading, you have an agent that models the environment. It'll predict, a S curve or a bear market or bull market. It'll go through the different markets. And it will say, hey, I see a little rise. It's rising by 1 point. I'm betting it's going to rise by 2 more points, then drop by 3. And then it will predict that, and then it'll actually see what happens. And then based off of the 2, it'll subtract it, and that'll be the gradient descent that it goes down to try to optimize its value. So model-based is always more powerful than model-free. And model-free is just random methods. Typically, it's sampling. You can do a lot of batching, so it learns quickly, but it only learns from experience. It's not very good for like self-driving cars unless you're doing an expert example where you drive the car and the model watches you do it, and then it tries to do it itself, and then you correct it every time it makes a mistake. And then if you use more powerful methods like a search tree, model-free can be better, and deep QN, like Q learning itself, where you just optimize the Q value, that's always model-free. So it has a lot of use cases. It's the most general of the models. One interesting thing you can do is you can actually combine the two. You can make the model simulate a reality, make the model free, learn from that simulation, and then give its value. Then it learns from that value and the prediction of the actual environment. So you can do like 3 times learning. Really reduces it. Some of the more advanced models like Reinforce and a couple other uses that approach, and it's good. It is usable in all situations. So anyone have any questions about that?
Yeah, the model is. I'm trying to understand that concept of model.
Okay.
The model, it's like maybe a set of differential equations or something that's actually able to predict how the environment behaves. Is that what the model is?
Yeah. So it's an iterative
Right.
policy that
Right.
every time it makes a decision, it tries to improve itself. So it's just like you cooking. You learn how to use a knife. You predict that if you go like that, it's going to cut. And then over time, you can predict the actions that you're going to make and what will happen. If you swing a bat and hit something, that's going to break.
The model was the knife will cut. That was a given.
Yeah.
Right.
Yeah.
But it didn't learn that. It has a model. It tells it.
Or it could learn it.
Well, I'm just saying in the model based, it's been told that it cuts. Okay. So in model free, one of the somewhere in there's some learning of a model, right?
It's random actions. So
Random actions, but there is a prediction of the value of the action.
after enough actions have been
Exactly. So it's learning a model.
Yeah.
Right.
So it's just experience. The only thing that
Based
is
on experience, it's learning.
that's
a
the
model.
only input though.
So I understand.
Yeah.
Yeah. Right. Okay.
Any questions about that? Because I kind of said, all right. Limitations and use cases. Reinforcement learning is always better with a neural network. So deep learning is always better with it. You can add any deep learning algorithm to it. It works with everything, including GANs. So you can generate data. It'll learn from the generated data. They can make predictions, and it can actually help the generative network learn to make the data better. And you can do it with CNNs. If you want to see, you're playing Mario, you want to take a picture of the screen and know what's happening on the screen, not just like the inputs. You can say, hey, there's a Koopa coming, I should jump over that. So the CNN in that case doesn't just classify things. It'll actually say, hey, I've seen this environment before, I know it'll happen, and then it tells the agent, hey, you should watch out for that. So you can add a bunch of different networks and get it working. But it's very hard to do. It's not an easy task, otherwise everyone would be doing it, because reinforcement learning can solve all supervised learning problems as well, including creating supervised learning models. There's this thing called NAS, which is a neural architecture search. And it will search a problem, and it'll create the optimal supervised learning algorithm to solve the problem, which is really nifty. The limitations are creating the reward function itself, doing the feature engineering. That's the biggest hurdle, always. Just creating the rewards. You making the goal based off of the rewards, escaping local optima. If you get stuck in a plateau because your agent isn't learning very well, you got to change up the exploitation. And then just you can also overfit, which is very annoying because it will just learn one thing. I had a tic-tac-toe agent learn, and because it was really dumb, which is what the really jagged thing was, it was stuck in a local optima where all it could do was do the same game back to back. and both agents did the same game no matter whose turn it was. So if one agent went first, it would do the same moves, and the second agent went first, it would do the same moves. So based off of how many times each person went first is who won the overall tournament. Real dumb. You want to always do something that encourages exploration where you don't get stuck. The use cases is very broad. This is just a couple I thought of. But you can apply it to pretty much anything, including health sciences and whatnot. But locomotion is one that was locomotion and advertising and genetics research are typically the biggest ones right now, and finance. Locomotion can be any type of locomotion. I saw a snake that learned how to move, which is really cool. You can learn robots. I've seen spiders. I've seen people swing and like go of ropes and catch new ropes. You can learn parkour, all sorts of weird, nifty things. Continuous learning problems, machinery. You know, if you want your car making device to pick up things smoothly so it doesn't jerk things around, you can actually let it learn to make gradual adjustments by adjusting the time steps. So if you want it to go smoother, you make the time step shorter. If you want it to go very quickly, you make it longer. And then, you know, production with the generative networks, you can make music, games, art, ray tracing for video games. You can create new characters. Video prediction. There is an agent that actually learned how to cook from watching YouTube videos, which is pretty nifty. That's all it did was just watch YouTube videos and watch people, because it had a structure classification engine. So it classified I don't remember what the name of it was, but used Adigrad to optimize it. And it watched the movements of the arms, and it actually learned how to make an omelet from nothing. So just a robot learned how to make an omelet. It's pretty cool. And then you can also, of course, do things like deepfakes, which are kind of terrifying, where you can also not only match the mannerisms of humans, but their voice and face, which is terrifying for the future, because you can create a video of someone committing a crime and make it undistinguishable from reality. And then you can have their voice, their face, all their actions. It's kind of scary. There's a lot of people researching defense against that.
Let me back you up.
Yeah.
Natural language processing.
Natural language processing. So it's basically supervised learning in that case, but it's better generalization. So reinforcement learning is used with a typical classifier.
So like sentiment analysis or something like that?
Yeah, sentiment analysis. So everything Facebook is doing, they're the ones, Facebook, Google, like all the billionaires in tech have a reinforcement learning firm that does their problems. So Google has the most expensive one because they bought like 7 different things. Then OpenAI with Elon Musk, and then Amazon and Facebook and whatnot. Facebook, you use the sentiment analysis and you can get the contextual meaning of everything, but you don't just use RNNs like typical sentiment analysis. You can model it to where it learns language itself. You can also program language, which is really nifty. They had it learn C, and they had it program something. Yeah. It's crazy.
So if you take just manual jobs, we're going to be eliminated by automation.
Oh yeah.
Think again.
Even our jobs.
Yeah.
Oh yeah. Not terrifying. What was I going to say? One of the nifty things about that is it learned how to write Shakespeare. And not only did it write Shakespeare, it wrote Shakespeare with actual characters, and it created characters that were consistent across the whole play. So
understood?
Yeah.
As a play?
Yeah.
Wow.
It had entrances. It had stage directions outside of the dialogue. It had dialogue boxes. It had dialogue where it referred to different characters between character interactions. It kept the characters throughout the entire play. Oh,
That's incredible.
Oh yeah. Reinforcement learning is really exciting. It's super interesting. It's the oldest, but it's only really had research done to it in the last 3 years. I think there was like 30 algorithms that came out last year alone, and people were still saying at the beginning of 2018 the evolutionary models were better than it, and then by the end of 2018 it was, I think, 13 times better in every use case than evolutionary models. So the progress made in reinforcement learning is just exploding out of its mind. Any other questions about the use cases and what you can do with it? Any thoughts? Okay. So here's where the deep learning comes in. Of course, you can solve everything with a good combination of neural network and agent. And here are the different types of agents you can use. I'm really just going to talk about these two, PPO and DQN learning today, because there's so much content in reinforcement learning. I didn't think I was going to get to most of it. I actually cut like 6 pages. Hey. But there's 2 different methods you can learn by. You can learn by optimizing just the policy itself, or you can learn by optimizing Q values. So those are the 2 different paradigms. This was the traditional use before computers for 60 years, and this is what's been used in the last 5 years, almost exclusively at this point. And actor critic is the main model that's used. So you have an expert critic that looks at the actions of the actor, which is the agent, and it goes, okay, you did that wrong, you did that right. It's like a director in a play. You know, as the actor does plays, it'll get experience, it'll learn how to act, it gets better at it. And then it can also get help from the critic, the director telling it, okay, no, you need to cry at that stage, you need to raise your arm, you need to be more theatrical. And that combination makes it learn very, very quickly. It makes it learn at a much higher efficiency than just Q learning in general. So these are all the actor critic models. So you got A2C, which is this thing that uses an advantage, which is calculating all the previous rewards it's ever seen. And then it sums it all up. And then it looks at the next reward, and it is a probability of the 2. So if it's a positive probability, if the new reward is better than the average of all the past rewards, it'll give it a positive advantage, where it's more likely to take that route in the future. If it's negative, it'll get a negative advantage. And that can cause problems where if it's so much more positive, like if it's 1,000 times more positive, your agent will become unstable, because no one can learn how to play Twinkle Tinkle Little Star and then go straight into Bach. You can't do it. I mean, you can try. That's what I did. I failed. It took a while, but it makes it unstable. It's a very hard learning curve. So one way to fix that is to clip the amount it can update by. That's what PPO does. So I'll talk about that next, I think. No, 2 slides. Then Q values is the standard. It's what it is used in every application. So it's like Java. You can use it in anything. It'll work in everything. It'll converge in everything. It might be slower. It might be clunkier. It definitely won't be as consistent as some of these other models. The 2 best models, if you want to learn 3 models in reinforcement learning, the only ones you need are deep Q learning, PPO, and actor. And actor and PPO are the best. And then just depends on the use case that you want to do. Actor and PPO came out at the exact same time, and on the Atari games, so it tries to learn how to play Atari games. They kind of flip-flop which one's better at each game. And PPO soars above it in some games, so I prefer PPO. You can also do curiosity learning in PPO, which is you give it its innate sense of reward. This is the best optimization for explore exploit, is you don't set the rewards for the agent sets its own rewards. So as it explores, it's like, hey, I've never been there, I wonder what's over there. It's kind of like you're playing Skyrim. You explore literally everything in the map, and it takes you 30, 40 times more, but you know where everything is. So the curiosity agent it's like, okay, I don't know what's up that ladder. I don't know what's in that chest. I'm going to go do it. Why not? And then dies, and it's like, oh, that was a mimic. That killed me. And then it doesn't do it again. And so that's really innate. That's how you can unlock use cases. I can see that being used in locomotion in different ways. Like, hey, how do I jump? I've never tried bending my knees before. Let me try bending my knees. I've never tried using my calves before. Let me try using my calves. So it'll learn how to sprint when before it couldn't. So curiosity learning is a great resource that's going to be used in the future. And then actor is just an efficient random sampling method that is better at PPO. In some use cases, like infinite use cases, it's better. It's much harder to train. Only the true professionals use it. And then here are some common tools that are usable. And I recommend, if you're a novice, PyTorch, because PyTorch is intuitive and it has the biggest development community behind it. If you look at all the Kaggle competitions for reinforcement learning, every top competitor uses PyTorch. It's just not even comparable. One of the other things is really good is Truffle, which I don't know why they said Truffle. I guess so it's pronounceable, but it's Tensor Reinforcement Flow Learning, which is real dumb. But DeepMind came out with that after Alpha 0, and they're like, okay, we created the best agent in the world. How can we help people with this? So they made their own library for Python, and I think they're implementing one for JavaScript. JavaScript works with all these as well. So all the APIs, you can do reinforcement learning in JavaScript. You don't have to know Python. Python's still better. It's easier. Much less workaround. You have to do a bunch of Linux commands to even get these to work for JavaScript, so it's just easier to do Python. Keras is just, if you know, like let's say I have a residual net or a recurrent neural network, and I'm not actually doing that much reinforcement learning. It's really a supervised learning problem, but I want to have some power behind it. Use Keras. It's just easy. It's high level. You don't have to know code for it. And then the APIs, this is where really reinforcement learning happens, is the GEN. Basically, you can train any network to do anything, and you can compare networks at the same time. So OpenAI made this environment where you can compete different algorithms at the same time. So you can do multi-processing of different algorithms to compare them before you do all the training time that's necessary, because reinforcement learning trains forever. So that is a must. And then RoboSchool is also really cool. And there's a bunch of, I have a tutorial at the end of this that you can go through, and it teaches you how to program robots with reinforcement learning. You know, locomotion, swinging, jumping, crawling, climbing, all sorts of cool things. Soccer, that's where the soccer tournament came from. Sprinting, tracing. RoboSchool is awesome. It has a bunch of hyperparameters that are easy to tune. So you just press a couple buttons, put in a couple numbers, and it trains everything for you. And DeepMind Lab, I haven't really done much, but that's Google's implement of just letting you use the Alpha family in their own environments. And then Horizon is a new one that uses actor critic models, and it uses a bunch of different languages for what their strengths are. So it'll use SQL, it'll use Ruby, it'll use a couple of different, I don't remember what the high level one is, but it has a bunch of languages all doing different things, and it makes it very quick to train. I'm going to work with that this week. I'm excited about that. That came out a couple months ago, so it's new. Any questions about these? Any questions about the policies? Because yeah.
Are you going to share these slides so we can?
Yeah.
Okay, cool.
Yeah, I'll be posting these slides in our Slack as well as on the Meetup page.
Okay.
Yeah, and I'll be in the Slack channel too if you have any questions about it. Like, I have all the books and everything else I use to learn, and all of them. So I have a long list of additional stuff. If you want to learn the math behind it, if you want to learn how to code, I have coding tutorials in it. I have all the math that you could ever want. I try to take most of the math out of this because it's just, you know, we don't have a lot of time. So,
Which, actually, speaking of that, we are at our
oof,
10.
man. Okay, so
any closing remarks?
Closing remarks would be, I guess, the future research. So one of the main things that we're trying to do is reinforcement learning, and is transfer learning. So training a model, having it know a domain, and then be able to implement it in different domains. So if I can train an agent how to play chess, can it play checkers? Can it play tic-tac-toe? Can it play Go? Can it play shogi? So that's one of the biggest things, and people have been able to do it for a couple things, but we're trying to get it to where this is the groundbreaking steps of AGI. So we're trying to get something that can learn anything, trying to make humans, and it's very difficult. And then partial information, which is a hidden work-off model. I didn't really get into that, but there's different implementations there that is hard. And then efficient sample learning. So just increasing the efficiency again and again and again, reducing computation speed. And then, of course, dimensionality reduction, which is very difficult for complex situations. So just, getting better at optimizing reinforcement learning. Any final questions? Okay.
Yeah.
Here's my number and email if you want to contact me about it.
Thank you, Chris. Thank you, everyone,
Thank
for
you.
coming out. Like I said before, if you're interested in getting tied into our community, please reach out to me and I'll get you added to our Slack. We meet every non-second Tuesday of the month at Belmont for our weekly meetups where we promote working on data science projects. We will help you get started on a project, help you kind of get your environment set up, we'll help you frame a project, or if you have a project you're wanting to work on, we can help you with that as well. Thank you for coming.
Great.
I tried not to go over. I tried to go hard.
5 hours not long ago.
Oh yeah.
Yeah.